oscillator, in particular for the chemical application of the harmonic oscillator, which is what we're going to focus on for the next 2 weeks, basically. I've spent the last couple of lectures just being very technical about our harmonic oscillator, our spring, our bond. And that's just to get us in the right place and to know kind of what the technical issues are. We're not going to do the same kind of analysis that we did for particle box. We will look at the wave functions. We'll kind of get a sense of how things are moving in the system and evolving in the system. But you're going to find that in some sense, the way that a bond works comes to energy eigenstates of the system, states of constant energy, it doesn't really look that much different from the particle box. All right, it's got a few other properties that are interesting. But we're not going to go through that rigmarole with calculating expectation values, averages of position and momentum like we did. It's very similar, right? We'll be able to do a lot of these things by inspection. So what I really want to transition into is applying this model to a bond. Right? We're going to work our way towards looking at identifying, in particular, the weaknesses and applying the harmonic oscillator to a real bond. Right? We'll look at its strengths. Of course, they're going to be really, really good strengths that are very, very helpful. That allow us to interpret vibrations. It works great, but there are weaknesses. Right? It's just an approximation. So we'll have to identify those weaknesses today. And we'll start to build theory that we'll revisit next class and also after spring break. That allows us to build up that theory. We'll kind of understand things from the perspective of a bond. So let's just recap kind of technically where we were. We've solved for this. Right, we have this spring of constant stiffness. Since that the bond exerts the same proportional amount of force depending on its displacement. Got 2 masses attached to it, right? We took that classical model of a ball, 2 balls with a spring. We said, hey, this looks like a diatomic molecule, 2 atoms of a bond. And we solved the Schrodinger equation for that, for the energy of that system. And we get these fairly complicated wave functions. But we're going to see once we plot them, they're really not that complicated. Right? They're really not that complicated. They just look ugly. And the idea, again, is that because we have a potential energy surface that's defined for all points in the box. Right, we have this quadratic potential. Right, our energy now, constant energy, we have, depending on the position of the bond, we have some balance of kinetic and potential, right? It's not just pure kinetic like it is inside the box, particle box. We have this trade-off of a constant amount of energy between kinetic and potential. They have different they have different features, different functions, and that leads to a wave function that doesn't look like a harmonic or like a particle in a box. It's not a sine or cosine anymore because you can't get a sine solution when you include the potential function. Right? Sine is only the solution to the wave function for a system without a potential. But what we get instead is a really lovely function that's in some sense even simpler than a sine or a cosine, or very similar. And we get this Gaussian function, this bell curve function, e to the minus alpha x squared over 2. Right? That's this bell curve. It has very, very nice properties. It's symmetric. It's even. The integral is a defined value, so you really don't have to do anything. The product of 2 Gaussians is a Gaussian. Right? So, which you can't say about sines, right? If you take 2 sines together, you don't get a sine out. You get sine squared, or you get some beating between the 2 sines. Maybe. Whereas here, you take 2 wave functions and you get another wave function out that looks exactly the same. So really, really convenient function. But the problem is it's not orthogonal, right? We have every level in some sense is if we just include the Gaussian, every level in some sense is connected to every other level. Product of 2 Gaussians is a Gaussian. So we had to include this additional function, these Hermite polynomials, these orthogonalizing functions, that ensures that each energy level is wholly distinct from each other. Right? And these functions are just polynomials. And so for each level of excitation V in your system, V equals 0, 1, 2, 3, 4, you have a unique Hermite polynomial that you multiply your Gaussian by. And they're just simple functions of x. Right? And you can just look these up. There's a lookup table. There's a way to calculate these explicitly. It's not a big deal, just a lookup table. And so the net function is right. So in the ground state, v equals 0, the Hermite polynomial is just 1, doesn't matter. So v equals 0 is just a pure Gaussian function. Right? It just looks like a nice smooth Gaussian. Really, really lovely. And in the next excited state, we get an extra x on the outside. We'll have to see what that does to the wave function, x squared, x cubed, and so on and so forth as we get excited. So there's a lot of terms, and of course there's also this normalization constant we add, which just makes sure that the square and the integral of the square of the wave function is 1. Right, so that just makes sure that our integral comes out to the right value. That's just a number. Right, so even though it's a little more complicated, it's really not that big of it's not a super complicated function. It's just one dimension. It's just x. And it's just a polynomial x cubed, x squared, x to the v times this Gaussian. I think it's more interesting to look at them physically, right? Let's look at a picture of them. And you're going to see that even though these look funky from the perspective of the particle in the box, which are sines and cosines, we're going to see that oscillatory behavior appear in these functions as well. They look like waves. What I've done here, hopefully everyone can hear me. It looks like we can. Yeah, great. Got a lot of people in chat today. So what I've done over here, this was something I wrote during office hours yesterday. Kind of find my mouse. Yeah, I wrote up a little program to just plot some wave functions for a harmonic oscillator, and I've put in some real numbers. Remember that let's just go back really quickly. Right, what are the only things that come from experiments in our wave function? Well, the only thing that really tells us what kind of spring we have is this alpha term, which is the force constant times the reduced mass. Right, so within the wave, right, every harmonic oscillator in some sense has exactly the same wave function. The only thing that's different is alpha changes, right? The type of bond and what you have attached to that bond is what's changing. Okay, so what I'm going to do is I'm just going to plug in some values for mu and k from a real molecule, just so we can plot this. So part of the homework is to do this process for a selection of molecules, and it's just algebra and calculating some numbers. It's really just, in some sense, this problem set is kind of an exercise in unit conversion. It's a lot of unit conversions. So what I've done is I've calculated from some physical parameters the k and the alpha for my system. Here's my k, here's my alpha. Again, don't worry about the formulas right now. And what I'm going to do is I'm going to calculate the energies of each level. I'm going to calculate the wave functions, and I'm going to plot them. Let me turn off the squared. So here I've plotted my potential energy. That's this quadratic here. It's kind of cut off. I can zoom out a bit. Zoom out a bit so we can see a little bit more. Okay, so this is like the first 20 levels of the harmonic oscillator. All right, so we've got our potential here. 1/2 kx squared, and each one of these dashed lines are our allowed energies. Okay, so this is v equals 0, v equals 1, v equals 2, 3, 4, 5, and so on. Okay, and what do we see? Well, if you notice, if you look at the wave functions within the potential, right? The way I like to think about a harmonic oscillator is that this is in some sense, a box whose potential grows. The size of the box is in some sense growing as a function of energy, right? As you start to stretch the bond further and further, your turning points get further and further. And so in some sense, your box is getting bigger and bigger. Right, so for each level, you have a different L in some sense. And what do we see? Well, within the box, we see the same oscillatory structure that we see for the particle in the box. Right? In the v equals 0 phase, right, we just have one peak. It's just a Gaussian. Right? That looks like a half period of a sine wave. If you look at v equals 1, which has an x times you get the x from the Hermite polynomial. Now that function's odd. It looks like a whole period of a wave. This looks like 1.5 periods, 2 periods, 2.5, 3 periods, and so on and so forth. Right? So even though this function is not oscillatory in the sense that it's a sine wave or a cosine wave, but inside of the potential, it sure does look like a sine or a cosine, doesn't it? Right? Very much so. All right, so it still has very much the same oscillatory behavior that we see in the what do you call it? In the particle in the box. All right, it's really not that much different. It's just that the functions are have a different form, but they in terms of behavior, they're exactly the same. They're orthogonal, and as you increase energy level, you get more and more nodes. Right, the frequency of the wave gets higher and higher and higher. Right, so let's just kind of look at the square of this, right? This is just the wave function. So what I'm going to do is I'm going to square the wave function. So we can look at the probability density, right? And it looks exactly like you would expect the particle in a box, except for one difference. Look at where the amplitudes of these waves peak, right? If you notice in the bottom levels, the most likely place for the particle to be in the ground level is right in the middle, right? Which is exactly like the particle in the box, right? The average position is right down the middle. If you think about what's the most likely place for the particle to be, right? What's the largest amplitude peak in the distribution? You can see that that peak kind of tracks along the edge of the box, right? And so what happens, what that means is, again, the idea is that as you put more and more energy into the bond, it spends longer and longer time at the edges, at the turning points. Remember that the way that the spring evolves is that when it's at the turning points, it has no kinetic energy. So it stays there for the longest amount of time. There's no velocity or no acceleration at those points. And at the bottom of the potential, in the center of the potential, it has all kinetic energy, maximum kinetic energy. So it's moving fastest here. Right, so if you have a particle that's traveling back and forth between the edges, system that's traveling back and forth between the turning points, it spends the most time along the edges and the least amount of time in the center because it's moving fastest in the center, right? So this, in some sense, shows us the same kind of behavior that we see for the classical harmonic oscillator, which says, again, is you have a very fast oscillating spring. It spends most of its time in the zero velocity state, which is the one at the turning point. And you can see that, right? The amplitude of the edge, the lobes at the edges are much larger than the ones in the center at the higher levels. Okay, so in some sense, it acts just like a normal spring does. But of course, the unique property of the harmonic oscillator quantum mechanically is that it can also exist some probability in the middle as well. And there's some, in fact, you sum over all the probabilities, more probability it's sitting somewhere in between if you sum over all these little lobes. But if you pick one lobe over another, if you will, it's obviously closer to the edges than it is in the center. All right, so this system, in some sense, on average, a standard deviation of the displacement gets bigger and bigger and bigger and bigger as V increases, energy increases. Right? It continues to spread towards the edges more and more and more. Right? That's a little different than a particle in a box. A particle in a box, in some sense, continues to spread a little bit, as you guys maybe saw in the homework, but eventually it levels off. Standard deviation of the position in the particle in the box reaches an asymptote. And this one does not. So as the energy increases, the oscillator will effectively, on average, spread out more and more and more, and it stays stretched bigger and bigger and stretched more and more each time. Because there's going to be more emphasis on the edges than in the center. All right, so again, oscillatory behavior like the particle in the box, but with slightly different physics, right? This system actually prefers to sit along the edges, especially at high energy. Right, that has really, really important consequences in chemistry. Right? You have a system that prefers to be really long, in some sense, at high energy than to be short. Right, that's going to make it really easy to pluck an atom off in a reaction, for instance. The other thing that's different, and you can see that quite clearly here, is remember in the particle in the box, the probability of seeing the particle outside the box, outside the potential, is 0. So remember, in the particle in the box, all the wave functions go to 0 at the edges, at the turning points, if you will. They very clearly do not here. right? You can see that there, this is psi squared, so it's the probability. There is a little bit of leakage out here. And you can see that there's a little bit of non-zero probability outside of the potential. And in fact, it gets, you can see it really here, really quite obviously. And there's quite a bit of integral outside of the potential. And that's the unique property of the harmonic oscillator, is that this system is no longer defined between 2 points, 0 now, it's defined between minus infinity and positive infinity. In the sense that this is not a truly infinite straight up potential like the box. It doesn't go from 0 potential to infinite potential, right? So if you want, imagine that you have a particle in one of these lower energy states. And if it were a infinite potential like the box, you could never put more energy into it. You can never squeeze it a little bit, pull it a little bit more to pull it out of the box. It's just impossible to do that. It's infinite energy. But here, there's an energy cost. There is an energy cost to pull the system further past its turning points. Oops, sorry, guys. Weird. Oh, sorry. So there's some cost to pull the system out of the, there's some energy cost to stretch the bond past the turning points, but it's only finite, right? The energy for the, if you're in the ground state, the energy to get the bond to here is just this energy, right? It's where vertically the position meets the potential, right? So what that means is that in some sense, there's only finite, you only require finite amount of energy to stretch this past. You only need to put a finite amount of energy to stretch it past the turning point. And so by definition, the wave function reacts to that ability. Right? The wave function says, hey, I do have some probability, there's some capability for me to be beyond the points, the turning points, the classical turning points of the spring, because it only costs a finite amount of energy to do that. So what happens is that the wave function in the harmonic oscillator past the turning points, it doesn't go straight to 0, but it decays exponentially towards 0. Right? In some sense, the slope, the functional form of the wave function at the turning point and on looks like e to the minus x squared. Okay, and e to the minus x squared only goes to 0 at infinity. Right? It doesn't go to 0 quickly. It goes to 0 is an asymptote. So the only time that the probability is 0 is at infinity. So therefore, there has to be some non-zero probability for the spring to be longer than its turning points. And you can see that by the fact that there's some area under the curve outside of this potential. Right? That has very, very deep consequences for chemistry. Try to explain why that is. Well, imagine we want to break a bond apart and substitute one of the atoms with a new one. Right, so imagine you have this molecule like this, and it's got this chlorine atom sticking on it. And you want to substitute that chlorine with another atom. So what's a better worst thing than chlorine? OH. Think about this reaction. Okay, so let's just think very simply. All right, we can think about these are substitution reactions. So let's just do it very simply, right? Let's think about this in 2 steps. Right, one of the reasonable mechanisms for this reaction is like an SN1, where the chlorine bond gets broken, and then the oxygen comes in and fills the gap. Right, so let's just think of a very, very simple cleavage mechanism. And maybe instead of using negatively charged OH, let's use a radical instead. And so that we generate a chlorine radical instead. So what would this mechanism look like? Well, what would happen, you have to cleave this bond between the chlorine and the backbone. And then the OH comes in and replaces it. Right? That's a very simple reaction. Very simple. So what's the, in some sense, what's the rate determining step? What's the hardest step of this process? Well, it's breaking this bond. Right? Once you have a radical recombinations are barrierless, they're really fast. They happen spontaneously. So the rate determining step is this bond breakage. Right? So this is the rate, so this is the RDS. Right? And so in order to break that bond, we need to stretch the bond until it breaks. Simple enough. So let's say, for instance, that the bond energy for this breakage is delta E. Or let's say, so this energy on string. And so the question is if we're going to break that bond, we need to excite the bond with enough energy that it falls apart. Right? So we need to excite the bond, the vibrations of the bond, the string, so that it has enough energy in it that it falls apart, right? The equivalent amount of energy. All right, so what we can do is say that delta E is going to be equal to one of the allowed, should be around one of the allowed levels of the vibration. That's going to be h bar omega v plus 1/2. Right, so we could calculate the V required for reaction, which is the quantum number, and that's going to be delta E over h bar omega minus 1/2. And we're going to round this number up. Round up to nearest integer. Right, because V has to be an integer. So this is the required energy level. Okay. So we could calculate that. If we know how strong the bond is, remember this, the omega is the square root of the force constant divided by the mass. If we know the stiffness of the bond, we can calculate this number no problem. Right? In fact, you're going to do this, a very similar process in the third rotation of the lab this semester for iodine. So we can come up with that, right? And so let's just pretend that that number is like number 10, right? You have to put it to 10 levels. Right, so here's our bond distribution, our harmonic oscillator bond. And let's say you need to pump it to the 10th level to have enough energy for it to react, to break apart. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we're in this teal color. Right, so the system needs to be in this state to break apart. Well, here's the problem. One problem, first of all, right? In order for this bond to break apart, right? Imagine the x-axis here is the distance between the chlorine and the backbone, the little squiggle. Right? We're in the 10th level here. In order for that bond to be cleaved, we have to move the two parts effectively to infinity. Right? We need to move them far away from each other to really truly break that bond. So that chlorine has to leave. Right? How much energy is it required for that bond to leave? Well, it's actually infinite. Right? Because this system is bound to this vibration. And so you can imagine the wave function of this system, of this bond, is in the V equals 10 state, this one right here. And we're going to stretch it and stretch it and stretch it past the turning point. But the energy required to do that continues to increase. Right? If I stretch it out here, the energy that's required for me to stretch it that far is where this vertical line meets the potential, which is way up here, right? I would need to put all this energy up there to break it. Well, that's a real problem, right? That means that this bond won't break. It means that I've gotten it to the point where I've had enough energy that it should break, but the harmonic oscillator says I got to put in more energy in order to make it stretch even further, right? I've just generated 2 new turning points, right? But I want to move this atom, I want to disassociate it. I want it to go away. Okay, so here's the first problem with this approximation, is that this tells me that this bond will never break, right? Because as I start to pump more energy into it to break it, right, I move here. Well, I could very easily be in an energy level that intersects this. Let's say it's this one, right? So I could stretch it here, put that energy in, and what happens is the system ends up being at this new energy up here. It's still bound. It's just vibrating faster. But the atoms are still connected. There's still a covalent bond here, right? And if I wanted to stretch this and break it, it's just going to put me in another level, right? So there's no bond breakage predicted here. What this says is that the bond can have any energy at once. It just vibrates faster and faster and gets longer and longer and longer with more and more energy and more frequency, but it never breaks. All right, so I can't predict anything about reactions from here. It says that I never lose the bond. The bond is always bound. All right, so we're going to have to, what that immediately tells us is that there's something wrong about this model. This model does not predict bond cleavage. It predicts that every bond is infinitely strong. You can have a bond with V equals 10 million, and it's oscillating like crazy, but the atoms might be 10 angstroms apart, but they're still connected by a bond. And that's obviously not true. Like chemically, we know that is not true. It has to fall apart eventually. Bond's only so strong. But this says that a bond can contain as much energy as it wants. We've got a problem. But there is a small correction that we can take, a small little hint that might help us, is that if we want to break, if the system is at this energy level, and we want the bond to be in such a position that the chlorine is really, really far away from the backbone, meaning X is really far, well, there's still some probability outside the potential that the bond is that long. Right? So even in the harmonic oscillator approximation, there's still some probability that the system is stretched beyond its turning points at that energy. And so it very well could be at some points when the OH comes in, that the Cl is really far away and the OH comes in and slips in. And the idea is that the chlorine in some sense escapes from the bond out here, and then the OH comes in and replaces it. Because there's some probability that the chlorine will be far away. Okay? So that gives us a little bit of a hint that maybe the fact that these wave functions for our bond, they can extend past the limits that we would expect it, right? There might be some probability the atoms are really, really far apart, and that might give us some ability to actually pluck them off randomly and then put a new atom in. They just happen to be kind of far apart that the OH can sneak in. All right, so the 2 conclusions that we have here, I've put this in the wrong place, I'm sorry. So continue. Let me see what this is continued on page 9. This is just for my notes. So the observations, page 6. Sorry, this is just for my notes. It's one that the harmonic oscillator never breaks. All states of bond are bound. That's a really terrible way to say that, but that's all states of the bond are bound. Right? An unbound state would be where the 2 atoms are not connected anymore. Right? They're always bound up to infinite energy. This is not physical. All bonds must break. They better. Right? But we do have a little hint that even at finite energy, delta E, there is a probability, and it actually increases as V increases. That the bond is found extended far past its classical turning points or its classical limits. And the idea again is that if you have this potential and you have some energy level, here's our energy level at delta E, and it's got some oscillatory behavior. Maybe it looks like this on the inside. The point is that it goes out to infinity like this, and that probability that it will be longer than the classical turning points is this area under the curve out here. So this is probability system is stretched to a reactive length. Right. The idea is that maybe the bond kind of leaks so that it's long enough that effectively the OH can come in energetically favorably and replace the chlorine. That turns out to not be exactly the reason why, right? But it does contribute. All right. But we really need to solve this first problem. Right? The fact that the harmonic oscillator never breaks. Okay. By definition, it cannot be a physical model for a bond because a bond breaks. All right. So what we need to do is somehow recover our theory. We need to make an improvement to our theory and understand where the harmonic oscillator approximation applies and where it doesn't apply. And how can we, in some sense, analyze that slightly more complicated system where you have a region that looks like a harmonic oscillator, and then there's this region at high energy where it looks like a bond, where it breaks. Okay. So that's what we're going to tackle today. We're going to make a change to our potential. We're going to make our potential energy not infinite anymore in the sense that it just never breaks. Let's build in a breaking into our potential. And what we're going to find is that in some sense, if we are really low, we'll have this new model that says that low energy, when we're close to the ground state of the oscillator, you know, like a normal vibration, it looks like a harmonic oscillator. And then as you start to pump energy into it, it becomes less harmonic and eventually falls apart. All right, so we're going to have this smooth transition from harmonic behavior to what we'll define as anharmonic behavior, the absence of harmonic behavior. All right, so let's think about the chemistry a little bit. All right, so towards an anharmonic bond line. All right, so I want to think about what this function is going to look like at different length scales. All right, so let's first think around the equilibrium bond length. Did I define this? Let me double check that I define this. I don't think I did. Okay, good. This is a new term. R equilibrium bond length is a new term. We have a label for it. Label it R sub E, which is the bond length that minimizes the potential energy. We want, so when it's at low energy, it's at the bottom of the potential, right? Low energy, sitting down there like V equals 0. It looks harmonic, right? System is harmonic. All right, so that means that the potential where X is around R sub E looks like 1/2 kx squared. All right, so at the bottom of this potential, it looks like a parabola. All right, then as we start to stretch the bond, increase the energy of the bond, we're going to start to see deviations. Right? We're going to have to think about the two limits of those deviations, at long distance and at short distance. Right? I think that long distance is easier to think about. Right? So as x goes to infinity, right? So we're stretching the atoms out further and further and further, right? What we're doing is we're reducing the covalency of the bond. Think of it as a covalent bond, or any bond. Any bonds. Covalent means easier. Right? We're going to pull those atoms further and further apart, right? And eventually the electrons in one atom are going to stop talking to the electrons in the other one. They have some distance of communication. We're going to learn that in a couple weeks. But they have some distance of communication. So as we start to stretch a bond, right, the bond starts to break. And what that means is that the bond doesn't really retract anymore. In some sense, it gets weaker as it stretches. And eventually we stretch it so far, the atoms are so far apart, they don't talk to each other, and the energy doesn't change. So at really, really long distance, the energy required to stretch the bond becomes zero. Because you now have two free atoms. The two free atoms at a distance, there is no bond between them. So to move them freely, independently of each other, should cost no energy. Right? So at the limit of infinity, the molecule AB, right, this becomes an atom A and an atom B that are allowed to move freely. Free atoms. Right? And we know what their wave functions look like for a free atom. They're just free particles. Right? So their wave functions are 1 over the square root of pi e to the ikx. Right? Free particles. Okay. So at infinite distance, we go from two bound systems that have potential energy to two atoms that have no potential energy and just allowed to move freely. Right? And this also means that at this limit, the derivative of the potential, how much does the potential energy go as we stretch? It goes to zero. Right? It flattens out. Basically, there's no penalty to move two free atoms away from them. Right? They're just basically separate. Okay, now let's think about as x goes to zero. Well, remember what the two atoms really are when you think about it. Atom A has this positively charged center. And then a negatively charged exterior that's somewhat impengible. It's kind of transparent. This is negatively charged. Right, and we have another atom coming in, B, that looks exactly the same. Again, it might have a different charge in the right. It might have different charges, but structurally, it looks like a positive nucleus right in the middle with a bunch of electron density around it. Right, as the distance between A and B goes to zero, what happens to these two atoms? Well, the two atoms start to impinge on each other. Right, so as R goes to zero, they start to share the same space. Here's A, and here's B. Right, the negative charge density in some sense starts to impinge on each other, right? And we get repulsion, right? They repel. And in fact, the potential energy of this goes as R to the minus 10. So as these atoms close together, their potential energy does not go as R squared, X squared. It goes as X to the 10. All right, so what happens at really close distance is this potential skyrockets in energy. It grows very, very fast. And so you could say that, for instance, that the derivative at short distances of the potential, as x goes to zero, goes to infinity. Well, negative infinity, I should say. No, yeah, negative infinity because it's decreasing. Negative. So eventually it becomes extremely costly to push two atoms close together. Right? They repel each other. Like that. Okay, so we have two different limits, right? So at the close limit, when they're really close together, as R goes to 0, they go to infinity really fast. And then as x goes to infinity, the derivative of the potential starts to go to 0, which means you reach an asymptote. So it's asymptotic at the infinite limit. It just flattens out. And then in the middle, it looks like a potential. It looks like 1/2 kx squared. Right. So we have a potential that in some sense is quadratic at the bottom, and then it begins to deviate smoothly along both directions. So let's draw that. Here's my now let's do a better color. So here's my coordinate system. We'll plot the bond length R versus the potential. And I'm just going to extend this negative. We'll see why in just a second. All right, I'm going to define my energy scale slightly differently. All right, remember that in the harmonic oscillator, we defined V equals 0 to be the bottom of the potential. All right, so what I'm going to define V equals 0 to be is the energy at infinity. All right, when you have two atoms really, really far apart, the potential energy between them is 0. Okay, that's what we're going to define as 0. So what that means is that this function goes to 0 as R goes to infinity, right? I'm going to draw it in green. Right? So at this limit, it basically looks like a flat line, 0. All right, we'll define V of infinity equals 0, which means no interactions between atoms. And then at R equals 0, right, this goes as R to the 10th, right? So at R equals 0, this goes skyrocketing. Right, something like this. I don't want to make it negative. I don't want to do that. So we want a little curve, right? So this goes as, right, so V of 0 goes to infinity as R to the minus 10. All right, so it's got this big, sharp tail on the low end. And then we know somewhere in between, it looks like a quadratic function. All right, so bonds are attractive, right? Bonds are attractive species and they're repulsive. Right, the atoms are going to attract each other to form a bond. So this energy is going to go negative. Right, so down here, we're going to have the parabolic region that connects these two limits. Right, so it's a negative energy at this scale. We have something that looks, it's not the best picture in the world. That's fine. Get the idea. All right, so down here, let me actually clean this up. Let's go ahead and clean this up. You guys can draw it the best you can. And try to draw as accurately as possible. So the inflection point that connects it like that. Okay, much better. So down here, this is near the potential, so I can draw R sub E, our equilibrium bond length. I'll just draw a little line. This. Right, this is where our bond length likes to sit. Right, and this is V of R sub E. Right, that's the minimum of the potential. That's where our bond likes to sit. So down here, this looks quadratic. Right, so if I kind of like draw a little box around it in this region. This looks like 1/2 kx squared. Right, kind of in that region, right? And so this function kind of smoothly starts to deviate from a quadratic potential as you go this way. And in fact, you can show that it roughly that this part right here, where the inflection point occurs, this rolls off as 1 over r to the 6th. Okay, so you can see, so it locally around the middle of the bond, kind of the stable region of the bond, it looks quadratic. On the attractive end, it rolls off as 1 over r to the 6th. This actually comes from the van der Waals effect. The van der Waals force. And at high energy, it rolls off as r to the 10, which is electrostatic repulsion. This is a much more physical structure for our bond, potential for our bond. It predicts, there's a prediction that we can put enough energy into it and it breaks. And there's a very, 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 very strong repulsive wall on the short end that keeps the atoms apart. We have a special name for this potential. It's called the Morse oscillator. And the potential is written as V of r minus r sub e. Again, this is a function v that takes in the argument r minus re. So think of v of x. It's not v times r minus re. It's equal to this number d sub e, which I'll define in just a second. 1 minus e to the minus, no, sorry, not minus. Let me make sure let me just double check to get my signs right. Oh, yeah, thank you. The minus alpha r minus re, this whole thing squared. All right. Now you may say the way that we just argued this is that this looks like 1 over r to the 6th. This looks like x squared, r squared, and up here it looks like r to the minus 10th. Right. So why the hell am I using e and stuff like that? It's just a really convenient way to kind of bring all of this together into a single function. Okay. It's really not too hard to show that this approximation leads to this kind of structure. Okay. So just believe me, what this gives you this behavior, and I'll show it to you in a second. We can just quickly look at how this function works at the different limits. If r is close to 0 here, r minus re is a negative number, so this is e to a big number. So this ends up being some very negative number that you square, so it becomes a very positive number. So v goes to infinity as e to the r effectively on the short end. At long distance, this becomes e to the minus small number or big number, e to the minus big number. That's 1, e to the 0, big number. So that's 1 minus 1, 0, right? So this potential goes to 0 as r goes to infinity. And what this means is this d sub e number, what that means is actually it's the distance between this point and this point. So if I were to draw a little arrow here, this is the gap between, this is what's called d sub e. And this is the bond dissociation energy. This is how much energy you got to pump into the bond to break it. D sub e. The cool thing about this potential, as we'll see in just a second, is that these properties, alpha, right? So what are the independent variables of our potential now? Well, it's not just k anymore, or mu. K and mu fall into this alpha, as we'll find out, right? Just like it does in the harmonic wave function. K and the mu are in this alpha term. But we have this new term d sub e, which is something that has to do with the bond strength, right? It has some independent parameter of the bond itself. But this potential now, it looks like a harmonic oscillator at the bottom. And the idea is that as the energy levels increase, they're going to stop looking nearly as harmonic. They're going to be very harmonic at the low levels and then become increasingly anharmonic. And it turns out that by measuring how the anharmonicity turns on, we'll look at that in the next couple of lectures. You can determine this value. This value is determined by how anharmonic the levels are. And I haven't explained what anharmonicity means exactly, but we will in a second. What that means is that this value is spectroscopically determinable. We can do spectroscopy on the vibrations of this molecule with an infrared spectrometer. And by measuring this anharmonicity of it, which I'll show you how to do, we can measure d sub e. Right? So from spectroscopy, we can actually connect our vibrational energy levels directly to bond strengths. This is one of the ways that we learn about literally bond strengths, how many of them measured thermodynamically is through this process. By modeling how a bond goes from harmonic to anharmonic, and the rate at which it does that is dependent on its dissociation. So we can already learn some important chemistry facts from this. So let's think about how this deviates from the harmonic oscillator. Again, what we can see that is if I were to kind of overlay an equivalent parabolic function, 1/2 kx squared over it, right? The function doesn't so near the bottom of the potential, it fits quite well. But as the energy increases, right, the potential doesn't grow nearly as fast. And then on the long end, it grows too fast. Right, so down here in the levels near the bottom of the potential, the actual potential of the molecule and the quadratic potential look very similar. But as we start to go up in energy, right, they start to deviate more and more, which is going to lead to a change in our wave functions. And it's also going to lead to a change to our energies. All right, so let's see how that happens. All right, well, so let's think about it from spectroscopy. Right? This is the way we're going to think about vibrations. The only way we can really interact with vibrations of molecules is through spectroscopic information. So again, and we'll look at this very, very carefully the next couple of lectures, but let's just look at very generally. If we have a harmonic oscillator, the energy of each level V, I'm going to write as omega, not a square bar, sorry, but tilde on top of it. Right? Just remember that this is equal to h bar times the square root of k over mu. Right? Just going to put it into one little energy term times v plus 1/2. Right? And we saw that the energy level spacings between each level, the v and the v plus 1 level, is just omega, right? They're equally spaced. They're equally spaced. All right, so if I have a little energy level structure here, a couple of levels, v equals 0, v equals 1, v equals 2. The energy of the first level is at 1/2 omega. The next level is at 3/2 omega. The next level is at 5/2 omega. And the energy splitting between them is omega. So if we do spectroscopy, we'll have to think about how do we interrogate these levels with light. We'll come back to that. But let's say, for instance, we apply light at frequency omega. So we just jump up the ladder one rung at a time. The frequency of the V0 to 1 transition is omega. Right? So we see a peak at omega, energy or wavelength or whatever you want to think about. And then the V equals 1 to V equals 2 is right on top of it. Right? We'll see the line for the 0 to 1 at the same frequency as the 1 to 2. Right? Because they're both omega. So you could theoretically think, well, there's also a 2 to 3, a 3 to 4, a 4 to 5, right? They're all overlapping each other in the spectrum. You have all of them overlapping. That's more or less what you see in a spectrum. We'll look at some spectra next when we get back from spring break, or maybe on the next class. We'll see what this looks like. But what happens with a Morse oscillator? One of the things that you can show with the Morse oscillator is that the energy of the level, again, looks like the harmonic oscillator, V plus 1/2, omega V plus 1/2. But a new term appears, at least the next order, 1/2. So it was 1/2, yeah. Omega times this new parameter x sub e, and it's multiplied by V plus 1/2 squared. Right, so this new XE term, which you can measure with spectroscopy, is called the anharmonicity term. Okay. So now the energy levels, and typically, I'll just write this here, typically X sub E tends to be on the order of 1,000 times smaller than omega, typically. All right, so it's a really small correction. All right, so you add this new term, and it's about 1,000 times smaller in magnitude than the harmonic term. Okay, so the anharmonicity is very small and gradual, but it scales as V squared. Right, so the harmonics are linear in V, but the anharmonicity is quadratic in V. So as V gets bigger and bigger, the anharmonic contribution gets larger and larger and larger much faster. So as V gets very large, this term becomes pretty significant. And so if you do a little bit of math, just a little bit of algebra, what you find is that for the Morse oscillator, the difference between V and V plus 1 is omega. But it gets smaller each level by 2 omega x sub e V plus 1. So what this now means is that the levels are no longer equally spaced. Right? Each level gets, the gaps between each level get smaller, linear in x sub e. So instead we have, for instance, let's just go ahead and do our energy level structure again. First 3 levels. 0, 1, 2. What are the energy levels? What are the levels of these? Well, this one, so z equals 0, is going to be 1/2 omega. Minus 1/2. Did I forget something? Sorry, this 1/2 needs to go away. I apologize, guys. This is not here. Thank you. Sorry about that. 1/2 minus 1/4 omega x sub e. Right, and the next one is 3/2 omega. And then we have 3/2 squared, that's 9/4 omega xe. And then we have 5/2 omega minus, let's think about that. So that's 2. V plus 1/2. V equals 2. 2 plus 1/2. Oh, right. So it's 25/4 omega x sub e. Right. So what's happening is the energy levels are getting smaller and smaller. Right. So the spacings are now omega minus. Well, let me just write it like this. The spacing here is so it's 2. Yeah, it's omega 1 minus 2 x sub e. And then this spacing is omega 1 minus, let's see, 2, 4 xe. And so on and so forth. Yeah, 4 xe. right? So the energy levels are starting to collapse. They collapse, collapsing energy levels. Okay. So that means that the gaps between sequential levels are smaller than they were before. So in the harmonic oscillator, we do spectroscopy on this, delta V equals 1 spectroscopy, go from 0 to 1, 1 to 2, we just go up one rung of the ladder. All of these transitions, all these absorptions are at the same frequency. We're all absorbing at omega. But in an anharmonic oscillator now, each one of the ladders, in some sense, each rung of the ladder absorbs at a different frequency now. Right? This one absorbs at omega times 1 minus 2xe. And then the 1 to 2 will be slightly redshifted at lower energy at omega 1 minus 4xe. And the next one's going to be 1 minus omega 6xe, and so on and so forth. All right, so what we're going to see in an anharmonic oscillator is that these absorptions that correspond to climbing the rung one step at a time, this one gives us one line, and this gives us a progression of lines. And the distance between each line is a function of x sub e. So the bigger x sub e is, the more anharmonic the system is, the faster these levels split apart, and the more the lines split apart. All right, so by measuring, put our infrared spectrometer near omega, if we see one line, there's some other things that we have to deal with, but just kind of hypothetically. If we see one line, we know the system is very harmonic. But if we look at that, that near omega, and we see a progression of lines, then we know the system is anharmonic. Because that means that the energy levels, each rung is slightly smaller than the other one. Previous. Okay, so let's look at what this looks like kind of structurally, and then I have some pictures for you. So I'm just going to draw my potential one more time. And like that. So this is right here. Right, so I'm just going to kind of draw energy levels in this system. Right, so here's our V equals 0 level. Maybe it's right there. Here's V equals 1. Right, and as I continue to go up, right, the spacings start to collapse. Hey, bless you. 2 is a little closer. 3 is a little closer more. 4 is even closer. 5, 6, 7, 8, 9. Right? You just keep going, right? They continue to collapse. And then eventually, right, I'm just going to kind of do some dots. By the time we get to the top of the potential, I mean, there's one final level before the system dissolves, right? This is like, in some sense, the final level. There's a bunch of levels that are just really, really closely spaced. Very, very closely spaced. Right, so we have a set of closely spaced levels. And there's some special level which we can align to V max, which is this level right here, which is the final level before dissociation. Right, go back to our problem again. Remember that when we talked about that chemistry problem, we're plucking the chlorine off. Well, now we can identify precisely which level we need to excite to break the bond. Right? There is some finite energy level that the system is bound at, and every level above that is no longer bound anymore. Right? Because what exists at all the energies above V equals 0? This goes to V equals 0. Sorry, it's not asymptotically approaching that. Right? Above V equals 0, the system is unbound. You have two free particles. Right, so up here above the energy, right? So down here below, so at V less than 0, we have A, B bond, and at V greater than 0, we have A and B free. So this is the bound region here, and this is the free region. Right, what does the energy levels look above that limit? Well, there we have free atoms. Right, remember that the wave function up here is 1 over pi e to the ikx, 1 for each molecule. Right, and the energies of this are continuous. Squared k squared over 2m. Continuous. So up here above this level, we have a series of levels that are we just have this band of continuous energy levels, right, which I can just kind of draw like this, right? Just a band of free energy levels. So these are free particle energies, right? These levels here are A and B moving freely. And they're continuous. This is a continuous set of energy levels. All right, so this is why the Morse potential is really, really powerful and why it's a really, really good. There's other advantages to it we haven't really quite tackled in the next class. Is that this model now gives us everything that we physically want in a model for a bond. First of all, it shows that at low energy, when we're near the bottom, and where molecules kind of tend to exist at 300 Kelvin, normal molecules, they're just normal harmonic oscillators, right? One of the things we'll look at next class is how accurate is a harmonic oscillator. We'll look at that. We'll have to think about how accurate it is down here. How harmonic are bonds truly? We're going to see they're very harmonic in the V equals 0 level, right? We can get lots of really, really chemically relevant information by assuming harmonicity. But the idea is that the energy levels begin to collapse as the potential starts to swing out and become anharmonic, which is exactly what we see in spectroscopy. And there's also this finite limit to how strong the bond, how bound the system can be. There's some Vmax where the system, if you go to Vmax plus 1, it's now a free set of free particles. And there's a set of free particle kinetic energy states above the potential that the system can exist in. These did not exist in the harmonic oscillator, because the harmonic oscillator, if we started here, just goes up to infinity forever. It should have already bothered you a little bit that the potential was defined from negative infinity to positive. Because if the bond, say the bottom of the potential is 1 angstrom, what does it mean for a bond length to be negative angstroms? Right? What does it mean for, I mean, it makes sense to stretch them, but it never made any sense really if you think about it. If the center of the bond is 1 angstrom, for the bond to be 2 angstroms shorter than that, that's a -1 value. That's not physically meaningful. So somehow built into the harmonic oscillator was this non-physical behavior anyway. We assume that the system can be at negative infinity displacement and positive infinity displacement. But no bond can do that, right? The shortest bond you can have is 0, effectively. And in reality, you can't even have that because of electron repulsion. Electrostatic repulsion drives the energy to infinity, right? You can never reach R equals 0. So the harmonic oscillator, just by definition, just doesn't work objectively. But as a limiting case, right, as something that represents how the energy works at low energy for the bond, low excitation, it works extremely well, as we'll see. And basically, the harmonicity just smoothly turns off as a function of energy. So it's very harmonic at V equals 0, V equals 1, and then as you continue to increase V, it becomes less and less harmonic smoothly. It's a smooth transition. It's not an on-off switch. It's a smooth transition between harmonic to anharmonic. Right, so this gives us everything that we want. This is a physical model of the bond. What we'll see is that most bonds, let's see if I can pull one up. Let's just look at an example. Let's just look at an experimental one, right? Maybe that's a good idea. See if I can find it. Okay, here's a great example. So here's some potential energy. These are, so I'm actually going to define a new term for you right now. So this potential, the Morse oscillator, is an example model, a model example, let me write a model example of what's called in chemistry a potential energy surface. Right, and that all it is it just tells you what the potential energy of your bond is, what the characteristics of your bond is as a function of its position. That's all potential energy surface is. Right, it tells you something about the energy of the system given the positions of the atoms. So people study these potential energy surfaces for all sorts of stuff. Molecules, reactions, very, very common. So here's a somewhat complicated picture. We don't really have to know everything that's going on in here. But these are different potential energy surfaces for HCl. And these are different electronic energy. Each one of these curves are a different electronic state. So we haven't talked about that yet, but the electron can get excited. So this X right here is the ground state. And this is distance. HCl internuclear distance. Right, so this one's way off. This one's way low. It's super stable. So let's not look at this. Is the first excited state, first electronic excited state of HCl. Right, and you can see that the behavior looks a lot like our Morse oscillator. Right, it's got this quadratic center in the middle. Right, here in the middle of the bond. These are experimental, by the way. They're determined experimentally through spectroscopy. There's a very, very sharp tail on the short end because of electrostatic repulsion. And you can see it has this inflection point and this slow roll off as it starts to disassociate to atoms. And in fact, it tells you exactly how it disassociates. When this goes off, you get an H plus and a chlorine atom that's excited in its first excited state. And it's a 2p. Or you've excited one of the valence electrons. And so this disassociates into that. Whereas you can see here, very interestingly, the ground state of HCl, you can't see the bottom of it or the top, but it's the same structure. It looks exactly the same as this plot, just deeper and less shallow. It dissociates into H atom plus Cl plus in its ground state, right? So you can see that depending on the electronic state that we choose for the atom, what the electrons are in, we get different outputs, right? We also get different bond strengths. Right? This is the bond. This is D sub E for the excited state. It's 1 point. It's about 2 eV in energy, and the bond strength for HCl is. Let me just actually quickly calculate it. I know it by hand in a different value. So let's just convert these to numbers you guys know. We haven't talked about EVs yet. So the ground state of this first excited state of HCl has a bond strength from 16 to about 18 here. So that's 2 eV. So let me just show you what that is. So that's about 193 kilojoules per mole. Right? So it takes about 200 kilojoules per mole to break the HCl bond into an H atom, an H ion, and a chlorine atom in its excited state. And then I know the barrier for the dissociation energy for this in a different unit, so we can calculate in terms of EV. It's about 42,000 wave numbers. Right, so it has, so regular HCl has a bond strength of 5.2 eV. Okay. So what that means is again, what's happened, and this is already some interesting information, we have anharmonic potentials for both the ground state and the excited electron excited state for HCl, and they have very, very different bond strengths. Right, this is 2 eV. So when you excite one of the electrons in HCl, you weaken the bond by over 60%. But in the ground state, like, this goes down 5 eV. Right, so it's a very, very deep, very harmonic potential, very, very sharp potential. And when we it goes to this dissociation limit, H plus Cl, it takes a lot of energy to do that, 5 eV worth. But when we excite the electron in HCl, we weaken that bond because we've excited the atoms. it still is bound in the sense that it has this Morse-like potential, but vis-a-vis is much smaller, right? And this is also a much more anharmonic bond because of that. It's a much more anharmonic system because the distance between here and here is much shorter than it is in the ground. You may notice there's some other levels here. And if you notice, these don't have the potential at all. They just go negative, right? They're just negative slopes. These aren't bound. So if I excite my molecule from X to one of these states, the molecule just falls apart. There's no more bond. So in HCl, there's really only 3 electronic states that have a bond, and the rest of them are repulsive and they fall apart. All right, so these are really important. This tells me everything about what HCl does when I put energy into it. Potential energy surfaces are super important. They're critical to understanding reactivity. And the Morse oscillator is the simplest example of one. Okay. So we'll look at this next class. We'll do a little more exploration of this, talk about some of the math, some of the spectroscopy, do a comparison and things like that. All right, have a good one, guys.
Whatever you got to say. Do it. Do it. Do it.